I've got a clicker. I've also got a laser pointer. I do not think anybody at the back can see the laser pointer. Is that correct? Okay. Yeah, I've got a different background to most people in our community. I started as a very bad physicist. And I don't mean the kind who gets to make atomic bombs, just one who was really bad at physics. I unfortunately work in cryptography because I do digital identity for a living. I started my career doing embedded systems, and there are aeroplanes on this planet that fly because I wrote the autopilots for them in Visual Basic. Quake in horror. I certainly did. It put me off flying until 2009 when I had no choice to get to the States but to get on a plane and risk crashing and dying. I also muck about with DNS provisioning, which is a really dull subject but very exciting to some of us, and network scaling. And I have the most highly questionable taste in music of probably the top 5% of the Go community, and I love that fact. Oh yeah, and if you want to get hold of me, I have a book on LeanPub, which I will mention again at the end. I have a GitHub, I have a SlideShare, and that's me. Or at least that's what I used to be, look like. I'm older than that now. Like hell would I be able to carry that off again. Right, so I'm going to skip through these slides really quickly. What is a collection is really what this set of slides is about. We've got a bunch of 5 different types in Go that could be called collection types, and the only thing they have actually all in common is you can range on them. The definition of a collection, as far as I'm concerned, is you can range the sodder. We've got arrays. Nobody uses them because who wants to have to keep defining how big something is? We've got slices, which do all the hard work of organizing arrays for us and create new arrays under the hood whenever we need them. We've got strings, which are arrays of characters. Well, arrays of bytes. Well, arrays of characters. Well, arrays of bytes. Yeah. That throws me from time to time, and we will have a little talk about them, quite a lot more, actually, later in the talk, because they're the weirdest collection to actually deal with. We also have maps. Maps also are really annoying in Go, and I'll get onto that as well. And then we've got channels, and channels are lovely, just don't use them, they're too expensive. Except when you should, when they don't cost anything. When this is actually turned into a workshop, it is actually going to gain a section on benchmarking, all the stuff I'm going to show, that will actually demonstrate why some things should or shouldn't be used in certain contexts. Like if you want to iterate over 1 million things, it honestly doesn't matter about pumping them through a map. If you're going to do it with, through a channel, if you're going to do it with 3 things, you're a muppet. Oh, but I don't know until runtime. Okay, that's why I often use reflection as well. Don't judge me. So, there's a lot of channel examples, because channels you can have so much fun in. But I'm assuming you all know all of this stuff. Why would you be at this conference if you didn't? So, I'm sorry, I've got to go back down there. It's too hot. And I can't really see that close up. Okay. So, we're all familiar with user-defined types. This lovely idea that we can define a type, give it a name, and put a function on it. That's the core, really, of most Go programming, is I've defined my own type, because I'm a bit of a type safety Nazi on this particular issue. And I'm going to give it some functions. And now I'm stuck with the fact that my function only works on this type. And that's the core point where everybody looks at every kind of generalization in Go. How do I get around the fact I'm stuck with this sodding type that does this thing, but I've got this other type that doesn't? That's the same underlying piece of data. So, we therefore have blank interfaces. I'm also going to skip a lot more of these slides because I can't remember what to say on all of them. So, okay. We have interfaces. Interfaces allow us to say, well, fine, given that you've got a function that follows a certain type signature on your type, give me any type you feel like, because I'm only going to call the function. I really don't care what that's doing under the hood. You know, and if you want to, you can build pathological types that do insane Rube Goldman sort of constructions with channels and network sockets and everything, and still make it look exactly like you'd make, well, I don't know, a string, from the point of view of a FUMP stringer. Somebody would scratch their head and wonder, why is it it's taking 15 seconds to figure out how to produce a 4-character string? Oh, because there's a network infrastructure in between. I can't see that. No, you can't. It's underneath an interface. See? They're a lovely idea. Right, and because of this, in this case, I've got an integer slice, I've got a float slice, And over here, I can use the same idea of a summable variable negation. And now I can put either one in, and I can sum it. For a lot of people, actually, that's as far as their desire for generic programming is ever going to go. Even though I look at that and I think, but why can't I put methods on a summable? Which is never going to happen. I've been told many times that's never going to happen. But it gets us off to a good start. Now, generics take the idea that I should be able to generalize my code in a slightly different direction. They say, well, you know what the pattern of the code you want to produce is. Why don't we kind of have a cookie-cutter templating system in a sort of not cookie-cutter templating system sort of way? So I can define myself an interface, and this is a radical innovation, which might one day lead to union types if we're really, really lucky, where I can say, OK, interfaces used to just be about methods, function calls. How about we make them about actual underlying type instantiations? You know, the stuff in memory that you really want to get at a lot of the time. So in this case, I'm going to put a tilde in front of all of these, wherever they turn up, because that tilde just says anything that is an int. Whereas if I just put int there, it has to actually be typed as an int. I mean, I've just divided the world in two between ints and things that are made of ints. And I don't like that. So all my generic programming examples are going to only use things that are an int no matter what type you think they are. Okay? And likewise, float 32s. So in this case, my summable, it only makes sense for numeric values anyway, so this is why I justify using a constraint. And my summable is going to say, give me any numeric type you can think of, and I will happily create you a sum function. And your sum function will then be able to do whatever you want in the places where you're going to use this particular type. So down here, I've this equals sign in the type thing. It actually means that islice is an alias for summable int, and fslice is an alias, rather than that islice actually being a type in its own right. So I can reference this summable int somewhere if I want to, but at the same time I can also reference islice, and they'll actually be taken to be the same type. If I actually just put type islice summable int, then funnily enough, an islice is now a summable int, but that's its physical underlying type, and it doesn't behave the same way you might expect it to, and it won't necessarily trigger type checks where you'd want them to. So, stuff you learn by doing stupid things. Right. Oh, I should really talk about this. So, all right, every single piece of code is going to show you what comes out on the terminal, because I'm kind of pathological about not doing live coding. And every one of them is a fully runnable piece of code, because I'm kind of pathological about the fact you should be able to run the code that's in a slide deck. So, no thought required, just plug it in and break it. Down here, you'll see that when I create a summable int slice, I can then call sum on it. When I create myself an islice, I can call sum on it, and so on and so on. This is very boring stuff. Things get a little bit more interesting, though, when we start thinking about generality in functions. So in this case, I think I would just like to write a function sum, that the person who's using it doesn't have to care about the types. As long as they're using types I've already thought about in advance. Oh my God, I've created another ghetto. Right, we're going to get out of this one eventually. So in this case, if you put in a value that happens to be a slice of float 32s, no, I'm going to, boing! Right, sorry. There's a reason people don't put me on this early in the morning normally. So, if I've got a slice of float 32s, I can do the whole code path based just upon it being float 32s. And then I can range through this slice. I can do my summation, and I can return my value, which unfortunately is going to come back boxed up in an interface, a blank interface, which means this isn't the sum I really want to write. But I can do the same thing with a slice of int, and anywhere in the runtime that knows it should be unboxing, like flump.printf, will correctly unbox down to the underlying type and do the thing I want it to do. But if I write code myself, where I really want to get at that value, I unfortunately still have to do a typecast. And trust me, even when we get deep in generics, typecasts aren't going away. I found edge cases. But over here, you see, we end up with, 10. Every single one's going to give you the answer 10. It's awful that all the answers are the same, because how do you disambiguate? You read the code. So, we can go a little further. Who here likes reflection? Yeah. Why am I not surprised? The second ever Go talk I gave, the first ever Go talk I gave is really funny because it only uses the blank interface everywhere. And it was for an audience of Rubyists in late November 2009. And it was like, my God, I found this amazing language. Look how I can abuse it by just never giving types. And it's sort of done in a 1950s cooking recipe book style that Apple had in Keynote at the time. And it's possibly the most disengaging code dive I've ever done in front of an audience. But anyway, the second talk I ever gave is exactly the same talk as today, except I only had one tool for doing it, reflection. It's basically, how do you write MapReduce with reflection? Well, we're going to be using reflection because it turns out there's still bits of MapReduce you can't solve with generics without the support of reflection. So what this talk is really about is, you need the lot if you really want to get very, very detailed in solving collection problems. And hopefully somebody will change that. So over here, the Reflex API is actually really easy to play with. It doesn't look like it if you read the help page. The help page gives you very few examples, and it's just, oh God, it's an unrelenting selection of methods. But in reality, whenever you want to do reflection, you want to take the value of something as far as the underlying runtime is concerned. Find that value structure. So in this case, whatever comes in here, I'm going to have a reflection value, and that's got all the type information, all the runtime information, everything in there, and some methods on it that might panic if you call the wrong ones, but if you call the ones related to the type you're dealing with, it'll be fine. Now, because of that, that means the next thing we always have to worry about is the kind of the thing that we're playing with. That kind is exactly the same as its underlying physical memory allocation type. Taking into account that structs sort of count as an allocation type as an entire family of structs, all count as the same thing. All structs, all are a struct as far as the runtime is concerned. This is as much as I know about the runtime because I refuse to look under the hood because who knows what naughtiness would then ensue. But anyway, so in this particular case, I'm interested in two particular kinds. I'm interested in an int, which actually to the runtime is an int 64 on my Mac, but it would probably be an int 32 if I ran it on an Atom netbook, for example. So int is a slightly funny one, but int is the one that everybody uses to cover all integers, because you always then convert back to whatever it is you really want. And so down here, all I'm doing is I'm saying, right, S comes in. What type is S? Okay, given what type is S, does it have any elements, i.e., is it an indexable type, like a slice? It does have some elements. Fine. What kind are the elements? Now, this is slightly naughty code because I should probably check that this will give back an answer. I don't know if it goes wrong if it doesn't because I just haven't bothered checking in this particular case. So down here, knowing that I'm using something that has elements, I can actually get indexes. But what comes back when I index is always another reflection value, i.e. another runtime type and properties description. So I'm going to pull out the int. I'm going to convert that to the kind of int I want, a proper platform-specific big int. And then I'm going to just add it to my value, and I'm going to have a result that will build up. And somewhere in, oh yes, up here I've specified what the type for x is. I can do the same with float32. I could do this for all the primitive types. In fact, if you ever write one of these and you're really anally retentive about it, you're going to need to write 21 cases. Which is one of the reasons I think why nobody actually does. I've got a couple of libraries where I have, just to show what it would look like, but sensibly nobody uses them, because it's like, who would understand them? Over here, so, all right, I want to sum a normal slice of integers. Boom, it works. I want to sum a slice of float32s, it works. Blank interface with some values in it, well, that's not numeric. This knows it's not numeric and even knows that those are numbers, but it says, no, the thing you're passing in doesn't deal with. We could sub-specify. We could say, we could go for each individual element as we went. We could check to see if we could type assert it. Oh, we can add that one. No, we'll ignore that one. So you could sort of lift a partial set of integers out of a blank interface slice. I wouldn't recommend it. And then we get down here, and we've got some custom types, which you'll notice are just, yeah. So, all right. We can rewrite how we would do that code so that we can take account of all kinds of integers, and we can take account of all kinds of floats. And we can actually say that with this value that we want to deal with for the return, we can create a new variable that happens to be of the appropriate type for the element, and then we can actually store values in it, either using setInt if it's one of the integers, or setFloat if it's one of the floats. So we can actually create a perfectly valid value there without ever once putting a type declaration in here for a specific type. But once you find yourself doing that, you're probably doing the wrong thing. I know, because I'm always doing the wrong thing. If you do code the way I do code, you're probably not doing code the way Go should be done, which is why these are always such instructive lessons, really. Don't do what Ellie does. Do what everybody else says don't do in what Ellie does. So, the great thing about generics, though, is I can make all of that problem go away. Because now I can have a function that knows about the numeric types I'm interested in. And it doesn't need to figure out what types are involved, because I can write it in terms of the types. Look, I've got a slice of numeric things, right? And I'm going to give back a numeric thing. So now I can just range over whatever that slice is, and I can kick out an answer. Boom, 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 boom. Now, that's kind of nice, but it does only work for slices, because of the way in which I've defined it. And we've got 5 different collection types, so we're going to try and tease all of them together until we've got something that can do all of them. Oh, what did I do different there? Oh, yes, and here I've been very explicit. I've said sum's going to be an int or float 32. But of course, we do have Go's type inference system. So a lot of the time, we don't need to do that. However, sometimes, if we're dealing with just functions as parameters, and we'll get onto that in a minute, we always have to specify, because it won't look at the function's parameters and figure out correctly the type, even though it knows them from the type signature you give it. So that's kind of weird. All right. This ranging thing, which is at the heart of collections. Effectively, ranging can be done one of 2 ways. We can either say, oh, you're a thing, you know how to kick me up all the values. Or we can say, you must be a sequence of things, please give me values in this order, I'll give you the value I want. So those are 2 ways we normally pull things out of collections. So in this case, I've decided to create this thing called an indexable. This is the point where I check, good God, I'm doing quite well. I'm roughly on time. So in an indexable, I have decided it would be really nice if anything that happens to be an underlying slice of whatever type I'm given, and you'll notice I'm not using a time constraint here, anything can go in there. Any kind of slice this gets is an indexable, because by definition, every slice can be indexed. That's the point of a slice. You give it a number and you get back an answer. And so I can write my own little append function here. Now what I'm doing here is I'm saying this append works on something that is pointed to of a certain type. And the reason I'm using a pointer is because obviously when we use appends for generic append, we get back a pointer from it that actually points, well, slice header more accurately. But anyway, it's early in the morning, I'm going to misspeak, there's going to be lots of bollocks, rubbish in this. So that will get edited out, I'm sure, like all the other ones. So this append will quite happily run append by dereferencing this thing, which we know has to be a slice because it has to be of type T. What about this E? The reason for this E is that I want to run this append for a particular instance, a particular instantiation of an indexable type, because I actually want to add a value to the end of the slice. To add the value to the end of the slice, I have to know it's of the same type as the slice. Otherwise, the runtime's going to say, bang. So this here allows me to say that I've actually not just got any old slice of T here, I've got an underlying slice of T that contains E's. And E can be any type I ask it to use. And this is the point where your head goes, and it's no fun anymore. We'll see a few more of these, but not too many, because I just don't like them. They make me think that I'm stupid, and I get enough of that just from Go to start with. It doesn't need more of it. So, I came to Go from Ruby, as I never cease to keep telling people when I'm drunk. And the reason I came to Go from Ruby was because you've got the best concurrency system of something that I could learn in one day. Oh, that means probably the best concurrency system. Because all the other concurrency systems take a long time. Well, the real concurrency system, please stand up. Coming from Ruby, though, it felt like I was being lobotomized, because Go's runtime does not use higher-order functions at all. And the Ruby style of coding is entirely higher-order functions, dressed up to look like there's objects involved, but we don't talk about that. So, higher-order functions is this really simple concept in computer science, that I've got a thing that does a thing. But rather than having it do the whole payload of the thing, I say it will take a function, and it will call that function, and that function will do the real thing, and it just all the boring boilerplate, like ranging or iterating or setting up network connections. So if anybody's ever seen one of my networking talks are often like 5 function calls deep in parameter. And you look at it and you think, oh, it's doing that, because you don't care about that and that and that. And sort of like, but if you write the same code in C, it's like, oh, 1,000 lines to do this, no 1,000 lines. We can do it in Go because we do have closures. But we kind of tend to not bother, which is really weird. So in this particular case, I'm going to define this lovely type up here, iterable. And iterable is going to range across the type it belongs on. And it's going to do that by saying, hi, please call my range method with a function that will actually do what you want me to do, rather than saying, oh, by the way, here's another value, you do something with it in your explicit code. So I don't have to manage the ranging. That's all taken care of. And then down here, I'm going to have a function that takes an iterable as a parameter and ranges through and adds things. Now, I've defined iterable to only work for ints, functions that take ints. Right? Standard way I might do this in Go 6 or 7 years ago, if I'm writing something quick, and on the one hand, I don't care about it being generic, generalized, and two, I'm going to rewrite the code anyway. This is code I've written so many bloody times in things. And it's just like, it's quicker to write it than it is to actually factor it out. So, down here, I'm going to have my slice of ints, my islice, and it's got its own range method. So this means for every type that I'm going to implement, I'm going to have to implement a range method for it, and I'm going to have to write this same bloody for I, comma, v, colon, equals range s loop for every single one of them that is actually really a rangeable object. And there's going to be a lot of code repetition across a code base. But still, the advantage is that when I call sum, I can give it a job to do. And somewhere around here, I do have a job I give it. Do I not? Okay, that's the point where my brain just went pop, because that example does blah, 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 blah. Sum, oh yes, I give it an iterable, that's that. I've hidden too much magic. See, it's all buried in the sum. The sum itself goes off and says, right, I'll just run this. Too early in the morning. All right. Now, the thing about this, right, it can't work with floats. Bang. And if we come over here, I wonder why that's blurry. Can everybody at the back actually read that? Excellent. I can't either. Right, I'll move further back so I can read it. Right, so over here, yet again, we're mucking around. We've implemented range for float 32s on f-slice, but yet again, they're not ints. It will go bang. So, we don't want that. This is part of this is what we're trying to get away from. We're trying to get away from having to care about those kind of details. That's what generics is for, not caring about that kind of crap. Now, this one I'm going to actually have to think about. I've got an iterator. I've got a range. I've got an islice that does the range. I've got a float 32 that does the range. I've changed the range so it takes an any. We look like we must be golden. Except, of course, when we now do this, you can't use a plus operator with an any, because any is not a numeric type. That's as far as I could get with the conventional Go type system for doing what we're doing, without some really weird, complicated tricks with lots of different functions and checking and stuff. So, I can't believe I put so many error cases in a row. I really must have been feeling mean at the time. Right, now we could try doing this with generics. So let's do a simple attack. I've got my numeric constraint. I've got my iterable that now works in terms of generics. I've even got my sum, which works in terms of an iterable of a constrained type. So all of this is golden, so we're not going to get the plus error. Right, type isolice. I've got my range function. But it's on integers. Why doesn't that work? Surely the runtime can see that that t and that int should be the same thing. No, it can't. It doesn't see it that way. So it's going to go bang. That bedeviled me, actually, in several other places later in this talk, where I'm already too deep in to be paying attention to what I'm doing properly. And it's like, why? Oh, God, no. It doesn't think it is that type at that point, does it? We have a solution to that later on. So, I can rewrite that, though. So I've got my constraint, I've got my iterable, I've got my sum, I've got my type, I've got my range. How is this now working? Actually, that's a good question. How is it now working? And then we've got an f-slice over here that's doing the same thing, and they've both got the correct types for their ranging. And then we come down here, and that's because I've told you what the type is. So this is the kind of case where you actually have to tell the generic that you're instantiating what type its parameters are. And if you've got multiple parameters, you might have to give it multiple parameters there. I think this is ugly, and I think type inference should be able to cope with those cases, but I can sort of understand that we're only halfway through generics really being where generics need to be anyway. There's another 10 years before we get the second half, I estimate. I mean, it took 10 years to get this half. Oh, it's all right. I mean, I've been a notorious critic of all of this stuff for years, so I'm allowed to get away with it. Higher order functions. Continue on with an exciting case. Now, what we can actually do, we can write a slightly more sophisticated sum method. In our slightly more sophisticated sum method, we will take anything, and we will give back anything. We've already got to give the type we're going to instantiate with. We don't actually lose anything by saying, well, you know what, I don't care what the parameters are. Why don't I find out at runtime what types I'm dealing with? Because now, whatever comes in there in any, that little s, I can do a type switch on it, and I can say, well, is it an iterable that's instantiated with the type I've been asked to use? Is it a slice of that type? And because I've actually defined the type in terms of numeric, and numeric only cares about the underlying memory implementation of the type, this will work. So now I've generalized the problem really nicely, I think. I mean, it's only taken me an extra, and a repetition and, Now, when we go through this, I can create a variable of the appropriate type in the particular case, because the type is known there. I can then do the ranging with the correct function created in my range for the type, not for the type that I would have been normally putting there. And then I can get back my answer. And so this is all golden. I love this, already. I've got more code, so I've probably saved my job for another 5 years because nobody's going to touch this. So summation is an example of a class of problems called reductions. I've got something that is linear. Well, it's not necessarily linear. It could be a vector in multiple dimensions if we really want it fun. But anyway, we've got a thing that is linear, and we want to turn it into a scalar value. We want to reduce the dimensionality of the thing. See, this is where physicists think. Computer scientists give you a very different outlook on this. Now, we're going to play with a little indexable again, and we're going to have a reduce method. The reduce method generalizes sum. And this is the reason why higher order functions are great. Sum is awfully specific to a particular problem. I can't reuse the code that's in sum for any other purpose than summing things. That's it. But reduce, I can take any old bloody thing I want, give it any old payload that I like, and it would reduce it correctly and give me back a scalar value. Lovely. So we've got another one of these type signatures, unfortunately, because we know that in this case I'm writing it in terms of an indexable, so we've got to say what the element type is to save it. But then over here we get quite a nice type signature. We've got a slice of t's. T's all contain e's, and I'm going to have a function that, given an e, which is the thing that I'm reducing into, and another e, which is the value I want to combine with it, it will give me back an e, this e here, right? And the e that comes back is the one that I can feed into the next run of this particular function call. So I can set it up as a little engine, or just churn and churn and churn. And then I will give back to the person who calls the function the final value. That there is the final value. That there is the function. This r is what that final value is at each step. And that v is the next item as we range through. This works beautifully whenever the type that comes out of a thing looks right for doing this. So down here, we end up with code like this. And anybody who's foolish enough to look in my GitHub will find lots of Go code that looks like this. It's very much a Rubyist way of writing Go. So I can pass in my function that will deal with integers for this here, this slice of ints, and I will get back the correct value. I can do it for float 32s, and I'll get back the correct value. I've put some little type signatures in so we can see what the types of things are at the end. Up here, we can see that it's the type we think it will be, because this is kind of a not very exciting thing to see. It's like, how do I tell them apart? Oh, look, they're different types. Okay. I can take reduce down the same route that I took sum, where I can say, okay, so let's figure out stuff about what you want us to reduce before we apply your function for doing reducing. And now I can have several different ways of meeting the requirement for doing it. We'll get some good examples of that as we move towards the end of this section. So up here, I've got my type switch. I go slice of ints, fine, I'll do all the bulletproof work. Oh, now what's this for? Well, if you notice, I've defined my function as any. Now, by definition, if I define my function as any, I'm going to have to put some type switches, or some type assertions, or something to figure out what the underlying type is. I have to do some unboxing. So for this one, I know I'm dealing with a slice of integers. I know that all the values in there are ints, and I'm just going to assert it's an int. And here I'm going to assert it's a float 32. If somehow this piece of code got run with something that didn't contain that, which it shouldn't happen in conventional Go, but you never know, hacked runtime maybe might kick the wrong type signature in, then it would go bang, and you would get a lovely panic, which you can recover from. Panics in type switches are recoverable. It's a bit like a rescue clause in Ruby, but even more obscure. So over here we do our reduction, and it works. It just works. I mean, I'm not going to even comment on this stuff anymore. All of these are true. They came straight out of my terminal over the last 10 days. They must be true. If we're really going to take this point of view, this is the point where we go, well, perhaps if I'm really going to have to do some type mangling, perhaps I'm going to reach for reflection to do my type mangling, because now I can deal with all the different types of ints, and I can deal with all the different types of floats. And so once we turn it into something that uses reflection, and this uses exactly the same pattern as was in the previous reflection example, I've had to lay it out slightly differently because obviously the code wouldn't fit on the line, and it's kind of ugly. I hate that. But anyway, it's doing exactly the same thing. It's getting the value out and turning it into an interface, then doing some clever stuff with it, and then bunging the integer version into the int or the float version into the float. Don't want to talk about that, really. It's not very interesting. We can do the whole thing with generics. And what's kind of, I think maybe I do like generics, right? So I will point out, I have been highly critical of the need for generics for years. I really just wanted to be able to put functions on interfaces. But now I think about it, I perhaps do like generics, because 3 years ago, I might well have written that to do something in something. There's issues with doing this. For one thing, this is about 20 to 200 times more expensive than not doing this, than doing it with types that actually were known. I've just turned Go into an interpreter every time I do this. And it's not an optimized interpreter. I'm running through a very unoptimized interpretation loop when I use reflection. Now, if I'm doing something that involves network lag, and what I'm doing on my box isn't an issue, I can, even if I used a completely unoptimized basic interpreter for doing it, I could probably still be as fast as my network on a modern piece of hardware. But if I'm trying to do something, on a slice is a very different beastie. It's right in memory. It's kind of offensive to say, no, please wait for, I don't know. I want to find out what kind of type you are, and I was thinking maybe somewhere between 85 and 120 nanoseconds. But I'm a slice. I can give you an answer in 0.3 of a nanosecond. Yeah, but, I want to make sure you're the right slice. Oh, please, it's quicker to panic and sadly, this is true. It's quicker to panic and recover. Because that's just a couple of stack frame unrolls. So, right, we'll skip on from that, because we don't really want to do that. No. But this, with generics allow us to do this. Look at it, look at it. And it's so simple. Who's going to open a page of code, look at that, and not know what it does? Well, I mean, compared to that, oh, wrong way. Compared to that, it's blindingly obvious. It deals with some T's, and it gives you some answers, and the piece of code to do it's really short, so it's very difficult to be confused by the piece of code. It's like a couple of days of playing with them, and it's the same as any other function signature suddenly, so it's great. Obviously, that goes through. I've used a type thingy for a reducible, and it does all the reductions, and it's boring. So, oh, what is interesting, though, apart from that, is that when you put out the type of the thing, of course, it's probably proper type. You can see exactly where it came from. I love that. I often print out types from printf and so forth, because the amount of times I do all of my debugging with printfs, because I never really got the hang of modern tools. And it's just lovely to have the type right in your face while you're doing it. It's like, oh, I know what I've screwed up there. So, I'd quite like to use my reduce with maps. Up until now, we've been using slices, and they are a very easy case. They're in a sequential ordering, and, don't have to worry about whether it's actually integer indexed or not. Now, reducing a map that's not indexed on a number is not necessarily a well-known and studied problem amongst practical day-to-day programmers. So we're only going to stick to things that could be a number for the actual key value. But we're not. And the reason we're not going to is actually the generic system gives us this concept of comparable. Any types in the runtime that can be compared to find out if they are equal is covered by comparable. So you can use strings. You can use structs. I don't think you can use functions, but you can use pointers to functions because pointer addresses are comparable and things like that. Now I've said that, I'm going to have to try it with functions when I get home, so to see if it's true. But anyway, down here I can now define my reducible in terms of a key and an element that's actually pointed to. And I can have a map of that key to that element, so I can write a reduce for that. Now, I could write a similar type signature that would sort of cover some of the cases with a slice, but not really. This is one of the things that bugs me. Slices and maps can't really act the same way. And this is the problem with collections in general. They all look like the same thing until you actually look at how they work. And this is true across all languages. They're never the same thing, no matter how much they look alike. Maps and slices are not the same thing. Slices and arrays are not the same thing. Strings and slices and maps and arrays are not the same thing. And channels are their own mad thing. But in this case, and we've unfortunately run out of color coding. So in this case, I've got this map reduce, well, this map that can be reduced. I mustn't say map reduce because that means something else. And if I run through my code, my map will successfully reduce. Same basic patterns. I've got my reducibles instantiated with its appropriate parameters, my function's doing all the right thing. That'll all work. Boom. Now, I can do the same thing on a channel. Boop, 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 boop. Channels, I need something to pump. So I've got this pump function. It just generates a sequence of values that go down the channel. And then over here, I launch it as a Go routine. That's the only exciting difference when doing examples with channels. They're fun to try and benchmark because you have to get both halves of them set up and doing their thing inside the benchmark. And if you do micro benchmarks, the stop and start on the ticker takes longer to do the stop on the ticker than the amount of time it takes to do the setup. So it's best to just do the setup outside the benchmark loop, cross your fingers and hope. And then inside, blat things back to their zero values, which, that bugs me. That really bugs me. I write a lot of benchmarks, and that really bugs me. So here, we've got a reducible that's a channel of T, and we're going to do our reduction. Yet again, it does it over range, boom, 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 runs down, 2 different channels, ints, floats, 32s, all works exactly as intended. So we found a pattern that seems to be working, and it's quite useful. But how do we generalize this? Well, for these 3 cases, it's actually really easy. And in fact, I'd love to be able to have another way of generalizing the concept of map, channel, and slice. So I could write this as a single case that would then go, oh, you mean map of such and such thing, or slice of such and such thing, but that we do not have yet. But when I stick my values in, boom, 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 it will all work. So this single reduce function can now take a channel of type T, a slice of type T, or a map of integers pointing to type T. So I think that's kind of neat. Unfortunately, the hoary head of reflection always raises itself at this point. Because I'm coping fine with things that are a normal integer with an index, but actually it's perfectly reasonable to say with a reduction operation, because it doesn't matter what order you reduce in. That's the point of these kinds of operations. That if you give me a map that's full of values of the right type, it shouldn't matter what order they're in, I should just reduce them. It's not like normally I would be doing all adds, or all divisions, or all multiplications, or all subtractions, or all something that is, in that sense, communicative. Commutative, even. So in that sense, I should be able to do it with every kind of map. So that's what I've done. And actually, once you're starting to do map indexing, there is a little gain by having the special case for ints. But I can save 4 lines of code by not, and it's only a little bit of overhead for using a map iterator in the reflection system. So in this case, the channel will work, the string will work. We're coming back to strings again. There's a place where strings will not work in this pattern. It's really annoying. And then we've got this with the maps, and boom, boom, boom. So we pump out channel values. I've wrapped up all the boilerplate, which we previously had, so now we get the automatic pointing out and everything in a do reduce. I've refactored, in other words. And then down here, we get all the right answers coming out, map of int to int, map of string to int. Notice they both reduce quite nicely. So we've now generalized our reduction to deal with most of the day-to-day cases, because how many people really ever use arrays? I don't either. However, it does seem a bit odd not to actually allow for arrays in the same thing. I mean, the point of generalizing code is not to have to care. So in this case, say I've got an array with a single item of T, or another one with 2 items of T. Now, I don't want to have to write this out for whatever max int on my platform is, do I? I mean, that's going to be nuts. So there's got to be a better way of doing it than that. Well, this is a place where we can't do anything but reflection. There is no way to deal with all arrays of size 1, and all arrays of size 2, and all arrays of size 3 that doesn't involve us getting into the reflection system. Now, it's kind of perverse if you think about it, because the whole point of arrays is you haven't got to go via a slice header. You're getting directly at memory effectively memory locations. So they're faster in those rare cases where you would use them than using slices. Only a little bit, but they still are. And yet somehow, to be able to handle them as a group, we have to generalize completely, and now they're hideously slower. I find that quite interesting. But this will still work. We can put in any kind of size of array, and we will still get it reducing down correctly. Right. I might be mean and only go through reduce and not show you how to actually do the other half of this, which is the map operation, because time is probably going to run out. But anyway, so reduction, continued. We could, if we wanted, actually introduce the concept of a reducible that each thing would have, because generics now allow us to have, a separate instantiation of that for each time. So we could instead have a couple of slices we add in, and then our reduce could include a reducible case. I don't just go, anything that implements reduce correctly for a numeric, yep, fine, we'll deal with that type as well. Boop, 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 boop. What am I doing there? Oh yeah, that's my do reduce. How did I get it so short? Well, never mind. This, by the way, is what Go code should look like. The entire Go standard library needs to be rewritten immediately to use this style of function parsing. Trust me, you'll all like it. I don't think I'm going to win that argument, though. Right, over here, it's perfectly reasonable that even though a type might not be rangeable, iterable, it might be reducible. There are odd things that lurk in maths, and sometimes if you want to model maths problems, you find yourself playing in spaces that don't quite work the way that people understand, don't have the intuition for. And sometimes you will therefore find that it might make sense that something could be reduced to a value, but couldn't really be described as a sequence. The value that comes out will be from some values that exist within it, but they might be multidimensional, or they just might be weird. They might not be what you're expecting. So there is an edge case where you might actually want to have two different kinds of interface that you will accept. And at the same time, you might also want to take a boring old function of an appropriate return type that's just an indexable thing. Right, so if you do, there's a reason why I put those in, but I then left the code related to them out, but they would sit in here, just here, above this. Now down here, this function, it takes an int. We are assuming that a function that can take an integer parameter is effectively a view over a sequence. Because if you think about it, it's not really any different to an array or a slice, except that it doesn't have the answer for you immediately. It's saying, well, I'll work that out. So if we were to do memorization, which is a really popular thing in functional programming, where you store off values as you calculate them and keep them saved, we might have a function that took an integer index that would either run the function that calculates or would just give me back the pre-calculated value. And I have a fascinating talk on functional programming in Go that goes through all of that stuff. In this case, functions are a bit of a problem now. Functions are infinite well, mathematically, a function, unless it's given limits, is an infinite sequence. It just goes on until you run out of numbers, which is, well, a very, very long way away. So you can't just use a function like that in your code without putting some limitation on it, because, well, that's just taking your machine over and it's not giving up until the heat death of the universe or you pull the plug. It's basically I can't say it, it's in German, but it's Turing's halting problem. How can you tell when something would halt? Well, if it's an infinite sequence, you can't. You can't actually tell if it's an infinite sequence, in fact, until it's almost finished. Or in fact, until it has finished. And then, Right. So potentially, this is a lovely bomb in the middle of our program. We can't allow that to actually just go on doing it, going and going and going. So I have to step through this slowly because it's not color-coded for me to be able to know what I'm talking about. So it's a function. It takes an integer parameter. It will return a value of type t, which we've specified as numeric. And this is the trick. It will also return a Boolean value to say if it's finished doing the job. In other words, it's kind of like, I guess it's the function reduction version of cooperative multitasking. We rely on the job to tell us that it's finished doing the job. So please always make sure the job finishes doing the job when you write this sort of stuff. But down here, we run our loop, and you'll notice I can't range. There's no range on functions. And I've kind of lied, because I said that the collection types were the 5 that we talked about at the beginning. But functions are a collection type, if they're the right functions. So this function is a collection. We're going to iterate through it one step at a time. At some point, we're going to hit the buffers, boom, And then we're not going to be able to iterate anymore. And that's fine, because it tells us we've got this okay. If it's okay to use the value that comes back, now you could make it, is it okay to use the next value? But that's another one of those chicken and egg problems. Which do I want to look for? Should I continue, or have I finished? But either way, if it's okay, it'll do some more reduction. If not, it'll just break out of that whole for loop. And I'm kind of like a cat with a laser pointer. And then over here, I've decided it's about time we formalize our payload. I'm a bit fed up with keep writing the whole function down in here. So I've just decided that we might as well have a generic function called adder, which is of a numeric constraint, and then it returns you a function value that happens to do the correct job. Because obviously, functions are first-class values in Go. We should use them as first-class values because that's what they're for. And so down here, my payload gets added in by just calling the adder constructor with an int as a parameter, and says, right, that's its type, int. That's its type, float 32. You're now all far too deep into my mind. Therapy is available afterwards at very attractive consultancy rates. Now, if we look at this a little bit further, what am I doing over here? So, I've managed to now create a situation in which I don't actually have to give it the type of the adder. Instead, I give it the kind of value I want, I'll give it the function I actually want an adder for. So the function that I've got here, which deals in ints and returns ints, I pass that into adder. Now, it takes its main parameter t, is a function that takes a value of type I, which is numeric, and it returns me a value of type e, and a bool, and the e is also numeric. Kind of neat. I've separated them. They don't have to be separated. I could probably get away with having them both as e. But you know what? There's a lot of cases, like with floats, where I do not want to use a float 32 to index a slice. It makes no sense. So really, I do have to separate them for the general case. But if I was only dealing in ints, I wouldn't have to. So that's kind of why I created this kind of weird example, so I could show that off. Now down here, if I do a reduction on an adder based on that function, I get back my answer with int. If I do it on that function there, I get those back. And obviously, I could reuse those functions now because I've assigned them to something. But anyway, yes, we'll just run to the end of reduction. If you want to know how to do map, you're just going to have to read the slides online. So, because otherwise, we're going to be into your break. So this one. Now, in here, I've decided to introduce the idea of my own custom functions, right? Function types. Whoever uses function types? Excellent. That's much better than last time I asked that question. People are becoming civilized. A more civilized tool for So, in this case, I've got this enfunc. An enfunc is any function that's got an integer as its parameter to find out what the value at that point is, and that will return me a numeric value and a bool. So now over here, where do we go? I can have a case up here where I check specifically for enfuncs. Now this is interesting. You'd think that would match enfunc, but it doesn't, because even though I've got a t there, and a bool there, and an int there, that and that are not the type signature. Now that threw me very badly when I found that, because it's like, how can this not be the same type signature? That literally, well, not literally, that's the problem. It's not literally that type. So, blah. The one thing I really do want changed in Go, and have been arguing for 13 years, is that we could just have a decent literal form for functions that allows me not to have to care about function type signatures at all. It can't be that difficult to do. Anyway, when I run this, and I do it with my traditional functions I've been using, and I also do it with my enfunc, which I now have to specify as an enfunc, because I do not have a literal form for this that just says enfunc x, return x, right? But when I've done this particular bit of ceremony, you will then notice that out of the end, I still get my answers correctly calculated, right? So it's kind of neat. Functions are kind of slippery things, though. They can be very, very perverse. And if we're going to play with them, we might as well know what it's like to play with them through reflection. Because calling functions using reflection is obviously such a sensible way to approach code. How many parameters has it got? I know, I'll ask the runtime. What are those parameters? I know, I'll ask the runtime. Okay, let's do that then. I mean, if you wanted to, you could use this kind of perversity to sort of kind of fake multiple dispatch and all kinds of stupid things. I don't recommend it, because yet again, this costs about 200 times as much overall as just actually knowing your function signature. So it's fine if you want to write a noddy interpreter for something and you want to really sort of offload a lot of work into just that. So how does this work? We grab a value, we find out what its kind is in the runtime, and we find out it's a func. Ah, that's all right. I know that I can pump a func with integers, and there's a fair chance that if it will return me a Boolean value somewhere in its parameter outset, that must mean stop. There's no such guarantee. There's no guarantees at all of that. But if it did give me back a Boolean value in the right place, I might infer it sort of could do that. I mean, it might be sort of like, perhaps I want to just experimentally look down this function's values and see what happens. I mean, there's nothing wrong with asking questions, is there? So, we're going to need a little slice of runtime values, because our function is actually going to have to be given a whole pile of runtime values to actually then call. And I'm kind of lazy. I tend to reuse that slice for the slice that comes back of the answers from calling the function, assuming it doesn't panic. It'll often panic if it's the wrong kind of function. That's kind of fun. And then down here, I happen to know that the first parameter I'm expecting back in a well-formed function is Boolean. And of course, once you've got something boxed in an interface, you can then compare it to values. So now I can compare it to true. I don't even have to go .bool, which is just so gauche. And then down here, I can quite happily then calculate a value using my function up here if the first value I got back is actually assertable as type T, numeric. Now, this is beautifully perverse code, which I never expect to see in a live project anywhere on the entire planet. Otherwise, for God's sake, blow it now. I mean, it's just like, you know, really don't do this in real-world code. But you can do it, which is kind of amazing. And this will then, over here, quite happily run. You'll notice we're only using reflection to deal with these. Each one of these runs, each one's got a constraint. Nope. Each one is only going to go up to 5. And bam, not a single explosion. They all go through fine. So now we've managed to join the case of a bare function signature, like that or that, with the case of our own custom function signature like that. And that's kind of, I was kind of pleased with that. Now here, this is the full insanity of the reduce that we have produced. We have got a constraint where we say if it's any one of the set of numeric values, it's numeric. That's not going to entirely work everywhere that we would want it to, but okay, fair enough. We're never going to be able to find a slice that's not indexed on ints, so it will work fine for slices. Maps, we can now use any one of these types to index into, and we'll still be able to calculate through, and that's kind of neat. We've got an iterable, so if somebody has actually written a range function on something, we will believe them. We'll range the way they tell us to range. We've got a reducible. If somebody's written a reduce function, we will just ask them for the answer and say, fine, your problem, not my problem. You know what you're doing, obviously. I mean, basically, every time we use an interface, we're sort of saying that. And then down here, we end up with a beautiful little type switch. Now, this might look like it must be very expensive in most cases, but actually think about it. I'm not mostly going to be ranging over 1 or 2 items. I'm not really going to bother doing this by using a function, unless I've maybe got 10, 20, 30 items. At that point, just the cost of the range already swamps the cost of doing the type switch. The type switches in Go are really cheap. They're not as cheap as like just direct memory accesses, but they're still cheap. And if you've got a big collection, 1 million items, you won't even notice the cost of the type switch in there, ever. In fact, at that point, The thing that will drive you nuts will be the cost of reflection if you end up using it. Now down here, we can cope with a string case. We can cope with a bare value. If it's a bare value, we just add it to R and we chuck it back. We can cope with slices, maps to ints, funcs to ints, channels. That's a generic reduce. The only way I could make this even more perversely generic would be to put in some cases here for some stuff from the net libraries and the HTTP libraries, which is probably another talk in the making. Right. There's one case here that's really nasty, and there's two here where, I'm sorry, I have to show it off. I just love the fact that you can actually inline an interface so you don't even have to give it a name, right? So nobody can even look through my documentation and see that interface exists, but I know it's there. I'm like Microsoft. I've got private methods, you know. Strings are a bit weird. Strings don't always do what you want them to do. When you're actually dealing with them directly, for one thing, they don't kick you back strings as part of ranging. What they kick you back is runes, which are int32s. And in some of my examples, well, all of my examples at this point, it wouldn't work, because I didn't have int32s until I gave the gigantic numeric constraint. And here you'll notice I've abolished numeric altogether. So how am I going to deal with the fact that this kicks out a very different type than I might be expecting? Oops, where are we? Ah, here. So let's skip through. Oh yeah, that's just to prove that that does work. Now, let's go through. Boom, 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 boom. You work, you work, you work. Oh yes. If I want to add 1, 0, 1, 2, 3, and 4 stored inside a slice, and I'm thinking of numbers, obviously I do have to subtract 48 from each value as I go, because obviously it's a rune up in, you know. But at the same time, let's say I wanted to, I think I've got a reflection example. Oh, come on. Nah, I held off the reflection example to a mapping. All right, forget everything I said about strings. They're beautiful. But do ask yourself what that is. Right. Oops, wrong direction. They should have put the buttons this way up, but the trouble is then the laser pointer would shoot straight in my armpit. It's not useful, is it? In this case, right, back here, oops. Nah, go on, that's it. Boop. In this case here, this can't actually work. Cannot use x, of type rune, oh God it is, as type t in argument. It's another one of those cases where, even though it actually is the correct type in the sequence, in the context, the generic system will not pick it up as the right type, no matter what you do. Unless, and this is really perverse, you box it in a blank interface and then type assert it. We can type assert it, it's the correct type. So whenever you want, these little edge cases pop up in a number of places. Whenever you run into them, this is the canonical, at present, solution to how you deal with that. I'd really like that to go away. I'd like there to be some way it just nicely does that anyway. Anyway, I'm going to drop you there, wondering how the hell do I now turn things back into maps and stuff. All the slides will be online later. There's another 20 of them or so, or something like that. I will skip to the very, very end, because obviously, whoever gives a talk that they don't at least attempt to sell something, that's where the code will be, that's where the slides will be. That is this, which hasn't had an update in 2 years, but I've got 6 chapters of code waiting on my hard drive. It's got to go in at some point. You buy it once for life. I'm only ever writing one book on Go, because God knows the world doesn't need me to do more than one. If you want to learn more about generics in a more practical and sensible way, Go by Example has some nice generics examples. I found this blog post surprisingly informative, which is not something I say of blog posts often. GoDev has a tutorial on them, and of course, Mr. Arundel has a very, very nice book on them, which I'm going to pimp just because I like him. He's one of those people in the community I've always thought was really good at stuff. Boom.